In linear regression, we used variability in one characteristic, like study time, to explain variability in another characteristic, like exam score. This allowed us to improve predictions by looking at conditional means of people who had the same characteristic. People who study a lot are likely to have more similar exam scores to each other than people who don't study much at all. What if we have even more information? Suppose we know not only the amount of time students spent studying, but we also know how well the students did on the midterm. Students who studied the same amount of time and got similar scores on the midterm are more likely to be like one another than students who only have similar study habits for the final but got different scores on the midterm, or who only got similar scores on the midterm but had different study habits for the final. We could improve our prediction of students' final exam score even more if we combine the information about study habits and midterm scores. Using several predictor variables simultaneously like this is called multiple regression. Just like in simple regression with one predictor variable, a multiple regression model specifies the conditional distribution of the outcome variable, like the final exam score, for all students who have the same values of the explanatory variables, students who have the same midterm score and the same study time. In the multiple regression model, these conditional distributions are all normal with the same standard deviation, irrespective of the value of the predictor variables. Moreover, just as in simple regression, the mean of each of these conditional distributions is going to come from a linear equation. But since we have more than one predictor, we have to expand our equation. Instead of just y equals alpha plus beta x, we add on another term, and we could add a third or fourth and so on, for as many predictor variables as we want. In this equation, we still have an intercept, alpha. Just as in simple regression, this is the value of y when all of the predictors are 0. But we have two slopes, beta 1 and beta 2, one for each of the predictors, x1 and x2. Suppose we're interested in predicting the selling price of a house. There are many characteristics that go into the value of a house. Two of these include the size of the house and the size of the lot on which the house sits. Bigger houses and houses with bigger yards tend to be more expensive, all other things being equal. We can find a regression equation that shows the relationship between price and both house size and lot size simultaneously. We might find something like price equals negative 10,536 plus 53.8 times house size plus 2.84 times lot size. Suppose we plug in 1,000 square feet for the house size and 10,000 square feet for the lot size. This gives us $203,131. In our regression model, $203,131 is the conditional mean for the distribution of housing prices for houses that are all 1,000 square feet and sitting on 10,000 square foot lots. That is, if you look only at the houses that are 1,000 square feet with a 10,000 square foot lot, and you calculate the mean price just of those houses instead of all of the houses, you'll find that the mean price is $203,131. Let's take a closer look at what those slopes mean. Here we have three variables, house size, lot size, and price. It can be challenging to visualize three variables at once. Instead, let's choose several values for lot size and look to see what happens to the linear equation. When lot size is 10,000, our equation is price equals negative 10,536 plus 53.8 times house size plus 28,404. But we can simplify this by adding the negative 10,536 and the 28,404, giving price equals 17,868 plus 53.8 times house size. When lot size is 30,000, our equation is price equals negative 10,536 plus 53.8 times house size plus 85,212, which simplifies to price equals 74,676 plus 53.8 times house size. And when lot size is 50,000, our equation is price equals negative 10,536 plus 53.8 times house size plus 142,020, which simplifies to price equals 131,484 plus 53.8 times house size. Notice that once we plug in lot size and simplify, we get a linear equation with just one slope and an intercept. The slope for house size stays the same no matter what lot size we plug in, but the intercept changes depending on what lot size we used. If we plot these three equations, we get three parallel lines. Each of these lines represents all of the houses with a given lot size. All of the houses on the red line have a 10,000 square foot lot, all of the houses on the blue line have a 30,000 square foot lot, and all of the houses on the green line have a 50,000 square foot lot. Each of those lines has the same slope, but they cross the y-axis at a different point. They each have their own intercept. Moreover, the distance from the red line to the blue line is the same as the distance from the blue line to the green line. That's because we increased the lot size by the same amount, namely 20,000 square feet, when we went from 10,000 to 30,000, the red line to the blue line, and from 30,000 to 50,000, the blue line to the green line. These three lines illustrate a key point in interpreting the slope in multiple regression. In simple regression, the slope told us the change in y for the change in x. In multiple regression, the slope is similar with just an additional twist. The slope tells us the change in y for a change in x holding all other variables constant. In our example, the slope for house size says that for all houses with the same lot size, like all the houses on the same line for 30,000 square foot lots, for all these houses with the same lot size, the price increases by $53.80 for each additional square foot of house size. That is, we pick one of these lines for a given lot size, red, blue, green, or a line for some other lot size, and considering only those houses with that lot size, we can ask, how much does the price increase for a bigger house? The slope shows us the relationship between the explanatory and predictor variables, all other things being equal. The slope in multiple regression tells us how the mean of the outcome variable, like price, changes for changes in a given predictor variable, holding all other variables constant. If a predictor in multiple regression has a slope of 0, there's no linear association between that predictor and the outcome variable, after accounting for the other predictor variables. But, just as in all of our inference, we can't simply look to see whether the estimated slope based on our sample is 0. Even if there's no relationship in the population, that is, if the population slope is 0, the slope calculated for any given sample is likely going to be a little bit off from 0. To make an inference about whether there's a relationship between the two variables, all other things being equal, we have to conduct a statistical test. The statistical test of a slope for multiple regression is nearly identical to the test of a slope in simple regression. The number of degrees of freedom for the sampling distribution of the test statistic is a little different, but we won't concern ourselves with those details here. But one key difference is the interpretation of the results. In multiple regression, the slopes describe the relationship between the predictor and outcome variables after accounting for all other variables. Making this caveat is important for interpretation of the results. Let's look at an example. Here are the results from a multiple regression analysis of the weight of 64 University of Georgia women athletes using height, body fat, and age as predictor variables. So we're using height, body fat, and age combined to make a prediction about the weight of these athletes. The point estimate for the slope of age is negative 0.96. This would suggest that for athletes that have the same height and body fat, the athletes weigh about a pound less for each year older they are. But can we really make this claim? It's possible that there's really no relationship between age and weight, after considering height and body fat. Let's look at the results of the statistical test. The software has calculated for us the test statistic, negative 1.48, as well as the p-value, which is 0.144. This p-value is greater than 0.05, so if there really is no relationship between age and weight, after considering the contributions of height and body fat, it would not at all be surprising to see a regression coefficient of negative 0.96 or larger. So, we conclude that age does not improve our prediction of weight once we've already considered height and body fat.